Hey everyone, it's Mr. Woodward. In this video, I'm going to do a projectile motion problem involving a projectile that's launched at an angle that we do not know. So let's take a look. While trying to capture a villain at his enemy hideout, James Bond drives his car off a ramp in order to get to the roof of the building. James reaches the roof perfectly at the peak of his trajectory. The roof of the building is 9 meters above the top of the ramp, and the ramp is 16 meters away from the edge of the building. You may ignore the height of James's car. All right, so first of all, we're told that James reaches the roof perfectly at the peak of his trajectory. So imagine that the building, here's the building, right, was not there. James's trajectory would then be kind of like this, right? It would go over the building and then come back down on the other side. And so when James reaches the roof, the car is going to be up here, right? And it will be like the peak of a longer trajectory if it were to extend past the building, okay? That means that at this moment at the top, there is only horizontal velocity, there is no vertical velocity. So the vertical velocity is 0 once the car reaches the top of the building. Okay, let's add some measurements here. We're told that from the top of the ramp to the top of the building, it's 9 meters. And we're told that the ramp to building distance is 16 meters. All right, so first question A, with what vertical velocity does James need to make this work? What vertical velocity does James need to make this work? So we know that James is going to be launched from this point vertically and horizontally. And so this initial horizontal velocity is unknown, and this initial vertical velocity is unknown. And we're eventually going to be asked to find those. So let's start with the vertical. Well, we know, that's the wrong approach. Let's start with the fact that James's final velocity squared is going to be equal to his initial velocity squared plus 2 times his acceleration times the change in vertical position. These are all vertical quantities, so I'm going to add y to this. Well, his final vertical velocity here at the peak is going to be 0, right? His initial vertical velocity is the unknown. That's what we're trying to find. His vertical acceleration is due to gravity, and then his change in vertical position from the moment right here that he releases from the ramp to the peak is the 9-meter measurement, okay? So I can multiply out 2 times -8, 9.8 times 9, and then subtract that, bring that over to the other side, and take the square root, and I get that the initial vertical velocity is going to be 13.3 meters per second, okay? So that means we have this one here, 13.3 meters per second. Question B, how long is James in the air? Okay, what's the time? Well, I could do this a couple of ways, but I'll choose just one approach. The final velocity is going to be equal to the initial velocity plus the acceleration times the time, and we're thinking vertically on all of these. Okay, the final vertical velocity at the peak of the building is 0. The initial vertical velocity we just found, 13.3 meters per second, accelerating downwards at negative 9.8 meters per second squared, and then the time, right? So this is the time that it takes to bring the velocity from this 13.3 to 0 at this point. How much time does it take to see that velocity change? So this time is going to be 1.36 seconds. 1.36 seconds. All right, and then how much horizontal velocity does James need to make this work? So now we're this, right? What's his horizontal velocity? Okay, let's try this equation in the horizontal direction. Delta x equals v initial t plus 1/2 a t squared. Okay, these are all in the horizontal direction. We know that the horizontal distance that James is going to cover is 16 meters from the ramp to the building. We don't know his initial horizontal velocity. That's exactly what we're trying to find, but we do know that his time in the air is 1.36 seconds. And then what is James's horizontal acceleration, right? This quantity right here. Well, one of the rules of projectile motion is that when an object is in the air, it's only being acted on by gravity. This is if we ignore air resistance. Gravity does not influence the horizontal motion. And so the car, James, will just move at constant velocity in the horizontal direction. That means that his horizontal acceleration will be 0. So that means this whole term just goes away. And I can easily solve for his initial horizontal velocity. 16 meters divided by 1.36 seconds tells me that off the ramp, he's got to move at 11.79 meters per second in the horizontal direction. Okay, so I'm going to include that one here. 11.79 meters per second. Okay, now I've included a bonus question. At what angle does the ramp need to be set, right? So here's one way to think of it. We've got the car sort of moving at this angle. It's going this way through the air, right? And here's the ramp. And here's the ground. And so we know this velocity, the vertical velocity, and we know this velocity, the horizontal velocity. And we can use those to find the angle. This would be the angle here between them. I'm going to call that theta, which is the same as this angle here, theta on the ramp, okay? So those velocities are, we've got 11.79 in the horizontal direction, and in the vertical direction, we've got 13.3. So we can set up a simple triangle, right? And here's our triangle. At this angle, theta, one leg of the triangle is going to be 13.3 meters per second. The other leg of the triangle is going to be 11.79 meters per second, okay? And so the angle is just going to be the inverse tangent of them. So we know that the tangent of this angle is going to be equal to the initial horizontal divided by the initial vertical, right? So this is the initial vertical. This is the, oh, I'm sorry, backwards. Initial vertical divided by initial horizontal. And so setting this up, theta, therefore, would be equal to the inverse tangent of the initial vertical divided by the initial horizontal velocity. So that's the inverse tangent of 13.3 meters per second divided by 11.79 meters per second. And so the angle that the ramp needs to be set at in order to make this trick work is 48.4 degrees. Pretty steep angle for a stunt like this. So if this stunt was actually going to be pulled off in real life, you'd have a stunt driver who would need to be on a ramp that's set at a very specific angle. And so physics kind of like this would have to be done in order to pull the stunt off.